Okay, today I'm going to say about subgroup. I think yesterday itself I told you, right? What is the definition of a subgroup? See, G comma star is a group. Okay, let H contained in G. Then H comma star is a subgroup of G comma star. Subgroup of G comma star if H comma star is itself a group. Is itself a group. But the thing is, see, if H comma star is itself a group means, so you need to verify the 4 properties: closure, associative, identity, and inverse. But what I'm saying is not all the 4 properties are needed. It is enough if you check 2 properties. What are those 2 properties? To prove H comma star is a subgroup of G comma star, comma, it is enough to prove number 1, H comma star is closed. Number 2, for all A in H, there exists A dash in H such that A star A dash equal to A dash star A is equal to E, where E is the identity element. Why two properties are suffice? I'm not thinking about the other properties. Closure, of course, is needed. Whenever you consider, see, you know G comma star is closed. Whenever you consider two elements from that, if you operate star between them, the final element A star B will also belong to G. But it is not necessary that the closure will also be satisfied in H. So for that you have to check it whether it is closed or not. No other. You have to consider A comma B, okay, in H, and you need to check whether A star B is there in H. Okay. Associative property you need not check because associative property will be inherited from the parent group. G comma star, it will be inherited because I told you associative and commutative are properties based on the binary operation. So whenever in G comma star, whenever star is an associative operation, automatically here also use the same operation, right? Star. So automatically it will be inherited. You need not check whether the elements are associative or not, right? And third one, identity you need not check because it will come from the inverse property. You just check whether for each and every element of A in H, there exists A inverse. So automatically A identity element will come. Can you say why? If for every A inverse is there, you know very well A star A inverse, A belongs to H, A inverse belongs to H. Automatically A star A inverse also belongs to H. So, but what is A star A inverse? You know very well that is there in G, right? It is identity. So identity is also there in H. So it is enough if you check only 2 properties. See, G comma star is a group, H is a subset. So to prove H comma star is a subgroup, it is enough if you check whether 2 properties hold good. The first property is H is closed under star. The second property is for each and every element in H, you need to have an inverse element. These 2 properties are satisfied, then you can say, see, that's why there exists a theorem. Let G comma star be a group. Let H contained in G. Then H comma star is a subgroup of G comma star if and only if for all A comma B in H, A star B inverse belong to H. Can you see here? Closure also comes here. Identity also, sorry, inverse also comes here. See, instead of saying I said two properties, right? Closure should be there, inverse should be there. Both can be combined and you can have a theorem like this. Proof is not needed, just you can say, right? If the elements are very less in number, even you can prove it is a subgroup. Right? See, for example, let us take some finite groups, right? Examples. Number 1. G is equal to 1 minus 1 I minus 1. It is a group under which operation? It is a group under what operation? 1 minus 1 I minus I.
Multiplication.
Multiplication. It is a group under usual multiplication. What are these four elements called? Actually, they are the fourth roots of unity. Because every element, if you are raising it to the power 4, actually 1 minus 1 I minus 1 are the roots of x power 4 is equal to 1. X is equal to 1 power 1 by 4. So these four elements are called fourth roots of unity. It is a group under usual multiplication, right? Now to prove, can you find two elements from this which will form a subgroup? Identity should be there, inverse should be there, something like that. Can you think by yourself and just extract a subset out of it, which is also a group? Extract a subset out of it, which is also a group. Yes, Nama, just find two elements from this. Of course, identity element should be there. You have to take from that. One more element I need, which will have inverse. Identity, I brought it. Take
1,
one more.
minus 1.
Yes.
1, minus 1.
1, minus 1. Very good. One important thing, order of the subgroup always divides order of group. There is a theorem. Wait, I'll tell you. You need not go for the proof of the theorem. Just every theorem, just read the statement. That is enough. 1, minus 1 is a subgroup. Good. Who was that? Hello. Who is that? Yeah. Somebody. Ram. Hey, Ram, you only asked something, right? You have posted some question in the group. I'm not
Yes,
able to understand. That's what I told I'll explain in the class. What was your question, Ram?
no, ma'am, that was regarding last class's question. So maybe I'll clarify that in the end of the class.
End of the class. Check. Okay. No problem. So, but do remind me, I may forget. Okay. So to prove h equal to 1 minus 1 is a subgroup. So there are two ways. First way is I'm going to use the theorem, right? Method 1. Right? To prove A star B inverse belongs to H for all A comma B belongs to H. See, in H you have only two elements, right? So either I can consider 1 comma minus 1 belongs to H. So implies 1 into B is what? Minus 1. So what should be B inverse? Okay, better I'll move to the other method. Then I'll come back. And form the Cayley table. That is enough. You learn any one method. Don't confuse yourself. That much is not needed for you. Okay, method 1. I'll form the Cayley table. 1 minus 1. 1 minus 1. Okay. Multiplication. Can you fill this? 1 minus 1. Minus 1. 1. Okay. So is this closed? Look into the four elements. H is closed. Yes. H is closed under multiplication. You have tried all the elements, all those things, right? The associative property holds good. Multiplication is associative, so you need not worry about it. Okay, what is the identity element here? 1 is the identity element. So can you say the inverse of each and every element here? Inverse of 1 is 1. And inverse of -1 is -1. Correct? Inverse of -1 is -1 is itself. Clear? See, -1 into -1 only you are getting 1. See, I told you once. See, whenever a group has even number of elements, at least 2 elements, the inverse of 2 elements will be they themselves. Clear? Hello? Hello?
Yes, ma'am.
So now it is this method you got it?
Yes, ma'am.
Check. Okay. I'll take one more example. Second example. Let G is equal to I 1 2 1 3 2 3 1 2 3 1 3 2. It is a group. What is this group? Why are you all sleeping?
Permutation group.
Permutation group on 3 elements, right? It has some other symbolic notation. What is that?
S3.
S3, ma'am.
S3. Am I going very fast? You are not able to understand, or what is the problem? Why you are not opening your mouth today? Still feeling sleepy? Hello? All are feeling sleepy. That is the reason. Say something, yeah. You can say, at least reply something. Whatever you feel, you say. What is the reason? We are all so dull today. What is the reason? No reason. Sure. Okay. So S3 equal to this. This is a group under, what is the operation here? Under S3 equal to G is a group under what operation? Huh? Hello. Okay, shall I cancel the class then if you are not comfortable today? Composition
No,
of?
ma'am.
No, ma'am.
Then please answer.
No,
Yeah.
ma'am.
It seems as if I am talking to myself. Right? It's a group under composition of functions. So I'll give you 1 or 2 minutes time. Can you find one group out of it? 6 elements are there. See, you have to find one subgroup out of it. And that subgroup order, the number of elements in that subgroup should be a divisor of 6 because the group has 6 elements, right? Either you can find out a subgroup of order 2 or order 3. Please, 1 minute.
And 2,
Yes, identity and
1,
come on.
2.
1, 2. Very good. Is she right? Either you can take I12 or I13 or I23. Because you know very well transposition, inverse of the transposition is itself. Good. So you can form a table out of it easily. Composition, I'm keeping a dot circle, something like this.
Ma'am, I couldn't understand. Can you please okay, again explain it?
I'll explain. See in the exam, I will not see you may not be asked to find a subgroup. You may be asked to prove that it is a subgroup, but just for the sake I'm asking. See, whenever you are extracting a subset from G, since you are in the process of proving that it is a subgroup, ensure that identity element is there, right? Then along with that, since I'm interested in a subgroup of order 2, I'm going to bring one more element. Okay, so that element should be its own inverse. So in S3, what are all the elements which are its own inverses? What are all the elements whose inverse is itself?
1, 2, 1, 3, and 2, 3.
2, 3. So along with I, either you can bring inside 1, 2, 1, 3 or 2, 3. Any one of these 3 you can bring out so that now you can ensure, yes, it will form a group. I'll try to prove this is a subgroup now. It is a group, it's a subset, so it is a subgroup. Right? So 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2 1 to I. So H is closed from the table. What is the table called? Cayley table. So from the Cayley table, H is closed. Composition of functions is always associative. Okay, then I is the identity element. Inverse of I and 1, 2 are they themselves or itself. You should not write R itself. 1 minute. What is the correct usage? How to write? R themselves. No, not correct. Okay, I'll write inverse of I is I and 1, 2 is 1. Okay, so therefore H is a subgroup of G. Whenever you speak subgroup, now under the same operation, you have to speak. Right? So one work now I'm giving you. Can you find out one subgroup of order 3 from this?
Yes, ma'am.
Let's take 2 minutes time. Yes, ma'am.
I 1, 2, 3 and 1, 3, 2.
Very good. So what is, because you know inverse of 1, 2, 3 is 1, 3, 2. 1, 3, 2 is 1, 2, 3. Inverse of I is itself. Clear? Good. Example 3. Yes, 3 equal to. I'm not going to prove that. I'm just giving it. Good, ma'am. Correct. 2. H is equal to I 1, 2, 3. 1, 3, 2 is a subgroup of S3. Operation and all I'm not specifying because you know very well only operation is composition of function. Okay. Okay, now I'll go to matrix group here. You know this is a matrix group. I told you, I asked you to check something out of it yesterday. I do remember. Somebody has written correctly, A, B, C, D, they wrote and they proved it. What is this? I asked you to prove this is a
Kleins 4 group under
Kleins
matrix
4 group.
multiplication.
Okay, I asked you to name them as A, B, C, D and prove that it is Kleins 4 group, right? Can you find a subgroup out of it? No idea.
Ma'am, 1001 and -1001.
1001 and -1 0.
01.
The subgroup, yes.
Yes, ma'am.
Yes. One more thing can you add, since it's a Kleins 4 group, with this, any of these 3 elements can be clubbed. Can you say why? Because all these 3 elements, they are its own inverses, correct?
Yes, ma'am.
See, if I name them as A, B, C, D, along with A, B is necessary. Identity element, no other go, you have to bring it inside. So along with A, you can take B or C or D. Just like you have seen there, right? Here also one, here Kleins 4 group is. Is there a Kleins 4 group here? No, not possible. For that you have to go to S5. Okay, that not needed for you. Okay, H is equal to 1001 minus 1001. This is a subgroup. This is a subgroup of G. Or even you can take this way. R is equal to 1 0 0 1, 1 0 0 minus 1, or h is equal to 1 0 0 1, comma minus 1 0 0 minus 1. All these are subgroups of your G. Clear? Am I confusing you? Am I going fast? Hello? Hello, bache. Clear? Concept is clear? I
Yes,
think you
ma'am.
Yes,
can
ma'am.
speak. Yes, you can speak
Yes, ma'am.
something. Are you doing something along with this? That is the reason why you are not able to concentrate. Some other work is going on? No. I think no, right? Okay, now I'll go for infinite groups example, right? Example number 5, infinite groups, right? So you know very well, Z is a group under which what operation?
Addition.
Addition. Is a group. What I'm saying is, to prove 3 times Z is a group. Yeah, what do you mean by 3 times Z? Yeah. See, Z has elements something like this, right? -2, -1, 0, 1, 2, 3, etc. So 3 times Z is, can you say what type of elements will be there? 0, 3, 6, 9, etc. And here also -3, -6, -9, etc. Only these type of elements are there in 3Z. I need to prove that 3Z comma plus is a subgroup of subgroups. So what I selected here, okay, is a subgroup of Z comma plus. Okay, how is that possible? Yeah, how to prove? So here you cannot go for Cayley table and all. Cayley table is only for finite groups. If you start filling the Cayley table, you have to go on filling, it will never end, right? Check. So how do you prove this? So closure. Tell me. How do the elements of 3Z look like here? Shall I take something like this? Let some 3m comma 3n belongs to 3Z comma m comma n is from Z. Clear? Is this point clear?
Yes, ma'am.
Yes, ma'am.
1 minute. How many are there inside the class first? So many of you are sleeping, feeling very bad. Okay. Okay, tell me. So I'm considering, why I'm considering 3m comma 3n. See, whenever m comma n is from Z, from 3Z you can expect only 3m comma 3n because they are all multiples of the elements of Z. So not all elements of Z will be here, right? Sorry, let 3m comma 3n belong to 3Z. Okay. How do you prove that it is closed? You have to prove that 3m plus 3n is also there in 3Z. I can write 3m plus 3n as 3 into m plus n. 3 into m plus n, will it belong to Z? So will it belong to 3Z?
Yes, ma'am.
Yes, ma'am.
It belongs to 3Z as m plus n belongs to Z, correct? Because every element of 3Z is of the form some 3 times an element of Z. So if m and n are from Z, m plus n is also there in Z. So 3 times m plus n will obviously will be there in Z. Okay. So associative property you need not prove. Why you need not prove? Because of what? So many times I insisted. What is it?
Addition is
It is
associative.
addition. Yes. Addition is always associative. Is always associative. You need not worry about it. Identity. What is the identity here? Additive identity. Same 0 would be there or not here? 0 is there or not?
Zero is there in 3Z.
3Z. Yes. So how to prove? See. 0 belongs to Z is the identity of Z comma plus. So now 3 into 0, 0 also belongs to 3Z comma plus. Therefore 0 is the identity element. Inverse. How do you say? So here there is something different. The usual Cayley table method we are not following. Everything should be said in a general way. I'm taking arbitrary elements here, m, n, like that. I'm not choosing a particular element here. So you have to be very careful. For infinite groups, no particular thing. Only generalized way you have to put. Right? Okay, inverse. Let Nama, tell me something. Let some 3 times m belongs to 3z. Arbitrarily, I'm choosing some element. Okay, so what will be the inverse of this particular element? Now, minus 3m, which is equal to 3 into minus m belongs to 3z. Will this be there or not? Since whenever m is there in z, comma, minus m is also there in z. See, how do you expect an element of 3z? 3 times any element of z, right? So I'm assuming 3m belong to z. I need an inverse for this. So I'm saying that minus 3m is its inverse. So, but how do I prove or how do I confirm that? I'm writing minus 3m as 3 into minus m. Okay. So whenever m is there in z, minus m is also there in z because z is a group under addition. So minus 3m, now I have written it in this format. 3 times any element of z. So obviously it is belonging to 3z. So therefore, for every 3m in 3z, comma, minus 3m in 3z is its inverse. Next, therefore, 3z, comma, plus is a group and hence it is a subgroup of z, comma, plus. Clear? Is this point clear?
Ma'am.
Yes, ma'am.
So in general, what I can say is general any nz, comma, plus is a subgroup of z, comma, plus. Okay, phi z, comma, plus is a subgroup. That type is subgroup. We can just assume.
Ma'am.
Yes, ma'am. Tell me.
Ma'am, initially you told that it is sufficient to prove closure property and inverse property, but here you have taken all the 4 properties.
Oh,
So in the
sorry,
exam,
sorry. Yes. I need not prove. Yes, you are correct. You are correct. I need not prove. I don't
so
know
in
why
the
I
exam,
proved
just
it.
2 properties will suffice, right?
Enough.
Okay.
I'm sorry, you need not prove it. Even identity, you need not prove. You can prove only these 2 properties, right? I'll make a note.
I'm saying the final conclusion should be right that it is a group or just a group part.
Can you please repeat?
In the final conclusion, you wrote that z comma plus is a group, and then hence it is a subgroup of z comma plus. So now we are just proving the 2 properties. So should we write about the subgroup itself?
Directly you can write it as a subgroup.
Okay, ma'am.
Check. Correct. You are right. Thank you for reminding me. Whenever, okay, G comma star is a group and H as subset, comma, it is enough. Check whether H is closed under star and for all A in H, comma, A inverse belongs to H. One minute. I didn't end the statement well. 1 minute. I'll rewrite the statement. The way it is written is not right. Let G comma star be a group. Okay. Just 1 minute. Yeah, I'll rewrite this. Includes H is a subgroup of G, comma, it is enough to check whether H is closed under star and for all A belongs to H, A inverse belongs to H. Clear? I've written a note. These two are enough. Okay. Cyclic group and are not necessary. Okay, something more I want to add. What is needed then? I need to say something about cosets. Before that, I'll say Lagrange is theorem. Cosets, right? Let G comma star be a group. And let H comma star be its subgroup. Okay. Then the set. Then the set A star H such that A belongs to G is called the, I'll explain, don't worry, is called the left coset of H in G. And the set H star A such that A belongs to G is called the right coset of H in G. See, what you are doing is already you are having a predefined what group G, and you also have a subgroup for that H, right? Now I'm taking that H and I'm going to operate every element of G with this binary operation. I'm going to apply either left side or right side. Okay, so left side if I apply, I'll get different sets. That is called left cosets. If I apply it on the right, I'll get different sets and they are called the right cosets. Usually these left cosets and right cosets, they partition the group. What do you mean by partitioning something? Don't worry, I'll explain.
Separate each other.
Will there be anything common whenever you partition something? Nothing should be there in common, right? Other than the identity. Check. See, not even identity. Nothing should be there in common. So note cosets partition the group. Partition the group. Don't worry about this definition. You can do an example, then you will understand the definition. Example, one example I'll do. No? Maybe I'll look into the time there. Let G be a group. You know very well, right? Under multiplication. And H is equal to 1 minus 1 is subgroup of G under multiplication. Okay. To find its left and right cosets. So to find the left and right cosets of H in G. Okay, first let us find the left cosets. So please listen carefully. It's very easy. Only thing is, just starting you listen. Left coset. Okay, I'll take H. I'll operate each and every element with this set. First, I'll find 1 into H. First element I'm taking. What is 1 into H? 1 into H means what? We have to multiply each and every element of H by 1. So again, we'll get the same element, same set, H. Correct? Hello? Hello?
Yes, ma'am. Yes.
Yes, ma'am.
Yes.
I can understand you're all feeling bored, but what to do? Minus 1 into it has lot of applications here. It has lot
And
of.
it is just complex to understand for the first time.
So you feel that I'm going very fast that you are not able to understand that.
No, ma'am. It's like it's for the first time we are like seeing this. No, that's why.
Abstract type of thing, right?
Yeah.
It is new, ma'am. That's why.
Okay, no problem. So minus 1 into H. The same way can you do it? Minus 1 into 1, minus 1 into minus 1. So minus 1 comma 1. Same thing. It is also again H. After I complete, you have to observe something and check, right? So I multiplied by 1, I multiplied by minus 1. Now I'm going to multiply by I. I into H. I into 1, comma I into minus 1. So I get I comma minus I. Minus I into H. So minus I into 1. Minus I into minus 1. So again I get minus I comma I. This is same as I into H, right? So actually how many cosets are there? Distinct cosets. If you say if at all they are distinct, 4 cosets I have written because there are 4 elements in G, but
Only
not
two
all.
are.
Only 2 are distinct. Okay, something you can observe. See, whenever I take 1 and minus 1, 1 and minus 1 are already elements of H, right? So even though you are taking that from G, it is already elements of H. So if you multiply by 1 and minus 1 with H, you will get back only H. Closure operation, right? You will get back H only. So they are same only. So that is your H, 1 into H, minus 1 into H, all are same. Similarly, I into H and minus I into H are same. So there are 2 distinct cosets. And what are the elements of the distinct coset? One has 1 and minus 1, the other has I and minus I. Actually, they partition the set, right? Suppose there are 4 elements, right? It is being partitioned like this. These 2 cosets do not have anything in common, but if you find the union of these 2 things, you get back the group G. So that's why it's called partitioning. Just dividing into 2. Dividing into 2 or 3. Dividing a room into 3, right? Nothing will be common. No common space will be there. So therefore, there are 2 distinct cosets, that is H is equal to 1 into h is equal to minus 1 into h, and I into h is equal to minus I into h. They're very important here. Every time I should mention left cosets.
Excuse me, ma'am.
Tell me.
Ma'am, I into H is different, whereas minus I into H is different. Like,
कहाँ पे different? Check करो.
okay.
Same
I,
element.
yes, ma'am. Yes. Okay, ma'am. Okay.
No problem. They are actually same, but they are written in as a set. They represent the same set, right? So now we'll find the right cosets. 1 minute. A time is there. Am I taking much of?
Ma'am, it's 8:47.
Sorry, right coset very fast. I'll write. Later we'll discuss. I'll write and stop. Right. Right coset na nothing, ma. H into 1. Right side I have to multiply. H into minus 1 I have to multiply. H into 1 and right side 1 into 1. Right side minus 1 into 1. So anyway I'll get H only back. Then H into minus 1, 1 into minus 1, minus 1 into minus 1. Anyway I'll get back H. Similarly, H into I. That is I into I. H into I, sorry. Left cosets and right cosets.
1 into I and 1 minus 1 into I.
1 into I and minus 1 into I. So again, you'll get I comma minus I. Similarly, H into minus I is equal to 1 into minus I minus 1 into minus I. Again, same thing, but in a different order. Same meaning. So here also H into 1, H into minus 1 are same. And H into I equal to H into minus I are two distinct right cosets. Distinct right cosets. Okay, you observe that here left cosets and right cosets are same, but it need not be the same in every case. So in which case it won't be the same? Why here they are same? This is your question. I have posted you this question. If you can answer today, now itself you can answer. Otherwise, you think and tell me tomorrow. Why here it is same, but it is not